So we call this integration by substitution, or U substitution, a lot of times people call it. And we looked at some, let me just briefly, I'll just step back a page or two here. Remember we did stuff like this, right? Like what would if we were trying to do this integral, what would our U substitution have been? Remember?
2x minus 1?
Yeah, it's right there, isn't it? Yeah. 2x minus 1, and the reason for that is, you kind of get a feel for this, but typically what you're doing is you're trying to pick the argument of some composition of functions. Like in this case, or in other words, another way to think of it is, what's complicating your life with this problem right here? Well, it's all this stuff inside the radical, right? That's what's making this difficult. If it were just a square root of, like x, or in our case, square root of u, we could just write that as a fractional exponent and use the power rule and we'd be done, right? So then whatever's the argument of that square root is the natural choice for our U substitution, right? And so we tried that. Remember, the quick refresher here. So we make our U substitution, and then we implicitly differentiate both sides, right? So the derivative of U becomes du, but the derivative of 2x minus 1 becomes 2 dx, right? And then, what I recommend you do here is then you say, okay, now, so our U substitution is, what's that going to do? Well, it's going to take all this stuff under the radical, and we're going to be able to rewrite all that stuff as a U to the 1/2. But what about the rest of the substitution? What else are we left with? Well, when we account for all that stuff with our U substitution, we're left with a dx, right? And we have to complete the substitution. We can't end up with a mixture of u's and x's. We got to go from all x's to all u's. And so we've got to somehow, we've got to turn this dx into some stuff in terms of u's. And so that's where, here's what we got when we differentiated, but all we really need is the dx. So to isolate the dx, we just multiply each side by 1/2. And we find out that dx is going to get replaced by a 1/2 du. We'll put the 1/2 outside and the du at the end. And then we've got a pretty easy integral to do, right? That's just u to the 3/2 times 2/3, right? So we've got our 1/2 times 2/3 times u to the 3/2 plus c. Done. All we have to do now is just reverse the substitution and rewrite our answer in terms of x's, and we got it, right? Okay, it sounds like a lot, but that's the stuff we went through on Wednesday. Now we left off with kind of a. We want to practice an easy one real quick before we move on?
Yeah.
Let's do that. Okay, so everybody, just try this one. Just try it on your own initially, and then if you need to compare notes with somebody, that's fine. Let's try, how about,
Are you serious?
I'm so excited.
That's awesome.
Yeah. Dude, I'll be there. I'll actually like this.
okay, try that. Try that. Now this is probably this is kind of a tough one. I mean, it's not super tough, but it's a little different than stuff we didn't look at one exactly like this. Let me just say it that way. Yeah. Okay, so you're gonna try picking your u, differentiating to find out what du is. and with, this is one that we could not do prior to U substitutions.
Okay.
So this is a good one to look at. It's one where we need our new trick.
U. X over 1. No, wait, X squared over 6. X squared.
I'm done. When you differentiate it, we're gonna get x squared.
Dude, I went hard. Yeah.
Okay, how about we'll just get one step collectively here and then let's keep going. What's our suggestion for our U substitution? Say, okay, say it again.
1 plus x cubed.
Good. Well, how come?
It's on the bottom, it's bigger, and when you differentiate it, you might get an x squared up.
Ah, okay, good. So we get that, all right. So it's on the bottom. Okay. Well, the whole thing wouldn't, then it's no different than just doing the problem, right?
Yes, I got that.
Okay, keep going.
Okay.
All right, let me write that a little better. Okay, so what's du then?
3x squared dx.
Good, so if we differentiate the left side, we just get du, right? If we differentiate the right side implicitly, so we're not differentiating with respect to anything. Derivative of a constant, 0. Here we've got the power rule, right? So we get 3x squared dx. Remember that you have the option. You could differentiate this with respect to x, and then just multiply both sides by dx to get there also, right?
Oh, okay. So that, you use an x squared dx, you take the 3 and divide.
Okay, so, right, so now look what we've got here. Let's just account for everything that we can. So this is just gonna be, all this is accounted for as a u to what power? To the -1, good, 'cause it's on the bottom, right? So that's taken care of. Now, how about, what are we left with? Well, we're left with an x squared dx that we've got to account for in our substitution.
Oh, let's go.
There it is, right?
Oh, we got this. Let's go.
Wow.
Okay. Right?
Oh, no.
So what is x squared dx equivalent to? 1/3 du. Yeah, so we can replace the x squared dx with our 1/3 du. Okay, so now what does our substitution become? Okay, so we get integral of, there's our u on the bottom, right?
So it's gonna be du over 3u.
Then on the top, yeah, on the top we get
Or you can take
du.
1/3 du, right?
Yeah.
And, okay, problem with that is, you guys can't do that integral, but that's how we'd set it up. We haven't learned that one yet. I think I forgot to write something down here. Yeah, I did. Okay, this is supposed to be a squared. Okay. That's okay though. On the bottom then we just end up getting a u squared, right? Everything else stays the same. Are u substitutions the same? Okay. Okay, this one we can do. Now, how would we do that integral? This goes back to, earlier stuff in this chapter. Well, how would we do that antiderivative there? Gotta rewrite it.
The u negative.
Yeah, it's just a power rule, isn't it? Right? So we end up with, this just becomes 1/3 times the integral of u to the negative 2 du, right? We could do that. What's that answer? We got our 1/3 out there. What's the power rule tell us? The indefinite integral or antiderivative of a variable to a power equals what? So here, let's just fill in the blanks. Up here, the integral of x to the n dx is what? X to the n plus 1 over n plus 1 plus c, right? Okay, so what are we going to get? U to the what power? Negative 2 plus 1 would be negative 1. Divided by negative 1 is the same as multiplying by negative 1, right? And so we just end up getting negative 1/3 times u to the negative 1. Well, that's just 1 over u, right? I could write that as, how about if we just do this? How about if we just write that as 1 over 3u? Right, plus c. Okay, last step. Yeah, reverse the substitution. What is u equal to? Sounds like I'm using bad grammar. U is equal to 1 plus x cubed. Okay, so we end up with our answer, negative 1 over 3 times the quantity, 1 plus x cubed plus c. Right? Okay, question time. If you didn't follow that, let's go back and see if we can figure out where things went away. Questions?
I just got confused somewhere in the middle, but I don't
Okay, so,
know where. I'm trying
So
to
let's-
find it right now.
okay. So, the steps, remember. So we started with this.
Mm-hmm.
We picked our U substitution, which made sense, and it might even just be an educated guess at this point. You may not be to a point where you say, that's certainly the U substitution. But remember, worst case scenario, you try it and it doesn't work, right? So you try something else, right? I mean, we want to pick this 1 plus x cubed because that's the complicated expression, relatively complicated expression that's inside the x squared. That's the internal part of that composition, right? The argument of the power function is the 1 plus x cubed, right? So that's a pretty good guess for our U substitution. After this, we're just going to differentiate. Now remember the trick, and let me just quickly refresh you on this trick. We could say, if this is U, then du dx is just 3x squared, right?
Yeah.
Would you agree? So if that's true, if I just multiply each side by dx, doesn't that give us the derivative in implicit form.
Mhm.
But you don't have to do that, right? You can just differentiate both sides without being, not with respect to anything, just differentiate using the derivative rules.
Mhm.
Okay, and we get to there. Okay, so if that's u, then this is the du that we get from that. Now we've just got to make our substitution, right? So if we go up here, well, there's our 1 over u squared, and then we're left with this x squared dx. Well, what's x squared dx? If du equals 3x squared dx, right?
Mhm.
Then I can just multiply each side by 1/3 to get rid of that 3, and I've got an x squared dx to substitute.
Okay.
And then we'll just put the 1/3 out front, because that's a constant,
Mhm.
and the du inside the integral.
Okay.
Right?
Yeah.
Now it's just a matter, and that's, that's not a trivial thing to do this. I mean, because we haven't done this, a lot of this maybe real recently, but whenever we see, remember the rule here, whenever we see a power on the bottom, right, we know to make that a negative power on the top and just use our power rule, whether we're integrating or differentiating. No matter which way we're going, we want to rewrite this so we can use the appropriate power rule. So in this case, there it is, right?
Mhm.
And then we just took the integral, simplified it just a little bit, and reversed our substitution. Okay? All right. Hey, I'll tell you what, let's do one more of those. Let's do one more practice. Try this one. Let's see. Oh, I have an idea of what I'm going to do.
Okay. At any time.
Okay, here's a good one. Okay, real quick, what do you think the u substitution is going to be here? U equals x plus 1. Good.
I didn't think at all.
Okay, what's that make du?
Wow.
Okay, good.
Oh, gosh.
Now see if you can go from there a little bit.
Is this hard one or
Guys,
just
not terrible. What's that? We'll see. I'm not sure. We'll get there tomorrow for sure. Okay, so if I make my substitution, what do I get?
X plus 1. No.
1 over.
Okay, so I'm getting a du over the square root of u. Yeah. Okay, so now this is one that we now can, we can do, right? We made a substitution that allowed us to take this integral or do this antiderivative. How do we have to rewrite it though so it looks like something?
u and make it a
Negative 1/2, good. So this just looks like integral of u to the minus 1/2 du So what's the power rule tell us there then?
2u.
Yeah, okay, good. It's gonna be u to the negative 1/2 plus 1, which would be positive 1/2, right? Divided by 1/2, but we don't divide by a fraction, we just multiply by 2. Multiply by 2, good. So 2u to the 1/2 plus c, last step.
2 square root u.
There we go. 2 times, what is u? Well, u to the 1/2 is the square root of u, right?
X plus 1.
And u is x plus 1. Got it? Okay. All right, so the one that we started, here's the one I kind of want to finish. Now, we started this guy, this is a little harder one, right? Because look what we did here. Let's kind of refresh where we were with this. We said, okay, well, first thing we might want to do is we've got that 3x that's inside of our sine and our cosine function. Let's let that be u. So if I make the u substitution, u equals 3x, then du just equals 3dx, right?
Mhm.
And so we could plug in for each of, so this is just going to become, whoops. This is just going to become a u. That's going to become a u. And this dx would then be 1/3 du, right? So there's our 1/3. There's our du. And here's our sine squared of u and our cosine of u, okay? Now what? We gotta substitute again. Now remember that when we say sine squared of u or sine squared of 3x, what that really means is the sine function to the second power, right? That's kind of our shorthand, but I think it's helpful when you're doing these problems, at least in your head, to rewrite this as sine of something squared. What that helps us do is it helps us remember or see visually, in this composition of functions, what's the outside layer and what's the inside layer, right? So what's the inside layer of this sine squared? Sine. Good. The outside layer is the square. Okay, and so then that is not one we can do yet, right? We need to, we need to still, maybe we could, but it'd be kind of hard. We'd have to expand this thing out, and we can do it much easier at the very least by making another substitution. So we could say, okay, what's the inside function there? Well, it's the sine u. Well, let's make another substitution, a v substitution, where v is going to become sine u. Okay? So if I differentiate, then dv is just cosine u du, right? Okay, and we'll make our substitution. So what do we get? Well, now we get, here is a v, right? And here is our dv, right? And so now finally this looks really simple. Now this looks like one we can do just a power, we'll just use the power rule, right?
Yeah.
We're just integrating this power function. So 1/3, what's the antiderivative or the integral of 1/3? 1/3 times the integral of v squared dv. The 1/3 we can keep out front, right?
Yeah.
So what's this going to give us though? So yeah, v cubed over 3 plus c, good.
Good job.
Okay, or another way of writing that a little simpler would just be v cubed over 9 plus c. Okay, so now what do? We did the calculus.
Substitute.
Okay, we gotta retrace our steps kind of, right? Reverse the process. So what's the first thing we'll do?
The sine u in.
Okay, good. So v becomes sine u, right? Okay, so this then becomes sine u cubed over 9 plus c. Now what? Okay, now we've got to reverse the u substitution. We'll replace all the u's with 3x's, right? And then we end up with sine 3x cubed over 9 plus c. And that's our answer. We could write this using our trig shorthand. We could move that 3 in there, right? We could write this as maybe something like 1/9 sine cubed 3x plus c, right? Okay, make sense? Okay, that's fine. Is there a way we could have maybe done this in one step instead of two? This is fine to do. If you prefer to do it this way, that's fine.
I like that.
You like that way?
Yeah.
Okay. Let's just quickly look at a way, I don't know if we can finish this, but we'll just look at a way we could do this. At the very least, I want you to see how this works. Okay, what if we just rewrote that as sine 3x squared, right? That's helpful. Could we do this with one bigger u substitution?
Yeah.
Suggestions what that might be?
Sine 3x cubed.
Yeah. What if we just took everything inside the power function here and called that u? So if u equals sine 3x, then what's du going to equal? So we get, we're just using chain rule now, aren't we? Right? We've got the sine of hand is just cosine hand times the derivative of hand. What's the derivative of 3x? 3 dx. Put the 3 out front, right? See how that works? Okay, that's kind of slick, isn't it? Now look what we've got. This becomes, all that stuff is a u. Now what about this stuff over here? What we're left with it, so we're going to get a u squared, aren't we? But we still have to trade that cosine of 3x dx for u stuff.
Make that a
1/3.
du direct.
Well, there it is right there, isn't it? Right? Okay, so our cosine of 3x dx is really just a 1/3 du, right? So we could write this whole thing then as integral of u squared times a 1/3 du. That looks familiar, doesn't it? Right, that's what we ended up with on the previous example. That's what we got in terms of these, right? Right, whoops, right there. We just did this in one larger substitution this time. Okay, so we know that answer, we already did it. That's just equal to 1/9 u cubed plus c, right? All we have to do is reverse that single substitution now, and we get 1/9. So u cubed, what's u cubed? Well, u is, remember, sine 3x, right? So this stuff right here then just gives us sine 3x quantity cubed, same thing as sine cubed 3x, plus c. Make sense? Okay. All right, so last issue, minor issue here. This one has some good news with it. This makes things a little easier. So let's just say we want to do something like this. Let's say we want to take the integral of x times the quantity x squared plus 1 cubed dx from -1 to 1. So we're going to do a definite integral. Okay, now, would you agree that with a definite integral, remember how we do definite integrals with the first fundamental theorem of calculus, right? We just do the antiderivative, and then we evaluate it from -1 to 1, meaning we evaluate it at 1 minus its value at -1, right? Okay, so suggest a strategy here. How could we do this with our new u substitution stuff? Okay, so we'll make the same u substitution we would have made otherwise. Probably u equals x squared plus 1.
Yeah.
We do the integral, then what?
And then we just take answers.
So we do the integral, reverse the substitution to x's, and then find our answer using the limits? Yeah, that would work, but I got a better deal for you. I got a much better deal for you. Watch this. If we, and this is really cool that this works. Wait till we see what this is graphically. So let's make our u substitution. And x squared plus 1, everybody agree?
Oh, yeah.
So what's du then?
2x.
Yeah, we're just gonna get 2x, then plus 0, right, all times dx. Everybody agree? Okay, so if we make our substitution then, we've got the integral of u cubed, and that's accounted for all this stuff, right? That's our u cubed, but we've still got this x dx. So what's that equal to?
1/2 d.
Okay, so there's our x dx. Is 1/2 du. Okay, but look what we can do here. What we can say is instead of having to go through the hassle of reversing this substitution and applying the original limits of integration, let's change them. We changed variables, let's just change the limits correspondingly, right? So really what we've got here is, this is the limit, the upper limit is when x equals 1.
Yeah.
Okay, but when x equals 1, what is u gonna equal? There's our substitution. Why does it keep doing that? This thing is just twitchy this morning. So when x is 1, what would u be? Yeah, 1 squared plus 1 would be 2, wouldn't it? Right? So the upper limit becomes u equals 2. Okay, what about the lower limit? Well, when x is negative 1, u becomes 2. Yeah. Okay, now, we don't even have to do anything here. If we're adding up the area under a curve from 2 to 2, what's the answer? 0. And we're done. And we could, I mean, right, we could do the integral and evaluate it, but we know that what this is saying is, we're looking at the area under this curve from 2 to 2 has no width, right? So it can't have any area. And the integral, we'd get that answer if we actually did the definite integral, but why waste time, right?
Wait, how do you get the 2?
Because if I plug negative 1 in for x,
Oh, I see them then.
right? Make sense? Okay, so what we just do, that is really cool. Okay, what we did there, I think, and this is really pretty remarkable. You get your first taste of making a variable substitution that changes the space in which we're working. So if we look at this, let's look at this area in 2 ways. Because this is pretty tricky. Mm-hmm. Let's try it. There we go.
I like the technical concept.
Okay, so let's start off. Let's look at graphically look at the area on the original function. Right. So we'll go up to y equals. Okay, we'll go up here, and we're going to look at the area under the curve. So y1 is going to equal that function, right? Okay, so x times the quantity x squared plus 1 cubed. Okay, let's graph that, and we're only looking from negative 1 to 1, so how about if we graph that from, well, I'm going to go from negative 0.5, or no, negative 1.5. I'm going to go up to 2.5. You'll see why here in a second. Okay, and then we'll just go zoom fit. Okay, maybe I better come back here a little bit. How about if we just go negative 1.25 to 1.25. And we'll I'll go zoom fit again. Okay, so if we add up the area from -1 to 1, remember we just go second, calc, and which one? 7, good. Okay, we want the lower limit. The lower limit's -1. Upper limit is +1. And there's the area we're adding up. It tells us it's equal to 0. How come? Yeah, okay, because the negative area exactly cancels the positive area. And we'll talk a little bit more, probably like Wednesday, we'll talk a little more about some properties of even and odd functions. It's just some minor league stuff. We've done all the major stuff. Okay, now let's do something else. So we've got this graph. Now let's graph this red one. Okay, what if I did instead? What if I did the function y equals, now we can't do a u on here, so we'll just call it x, right? So we're going to look at the area. I've got 0.5 times, I could put that 1/2 right in there, couldn't I? Right? Okay, so I've got 1/2 times x cubed. Okay, I'm going to turn the top graph off. Just leave the bottom one on. And let's graph this from -0.5 to positive, or excuse me, 1.5 to 2.5. Let's see what this looks like. Okay, well, we'll wrap this up Wednesday. That gives us a good start. Okay, I'll give you lab day tomorrow.